All right, guys, so this is our first chapter. I skipped chapter 1. It's an introductory chapter, and I just don't necessarily enjoy it myself. We go over all of those things anyway, so I just don't see the point in introducing it, kind of confusing you, and then going into further detail with each chapter. So we will just touch those things when we get to them. So the first chapter we go over is chapter 2. Miss Brown would probably know a lot more about this than I do. This is basic chemistry. So I always try my best because it's in the beginning of the book, and you do need to know some of these things to be more knowledgeable and to make things connect better for you for biology. So this is why this is the first real chapter that we have to go over. Also, my chair is really squeaky. I'm sorry. And my kids are being loud behind me, but it is what it is. All right, so before we move on, you always take notes during these things, during these recordings, or if I'm there, or if even Miss Brown's talking to you, you'll always take notes. Note-taking is something that I hope you get better at in this class. You cannot write down everything that's on a slide, and I summarize the slides pretty well from coming from the book. You can't write down every single word. So I know that all of us at some point in our lives have wrote down everything somebody's put up on a board, and then if somebody says, "Hey, what'd you write down?" You're like, "I don't know," because you didn't give your brain time to process it. So it's almost like a step system, and it's almost like absorbing it for the first time. So you have to actually read the slides or listen to me, comprehend the information, and then put it into your own words. If you're just writing down, throw a ball, pat your dog, rake your leaves. This is the first part of the sentence in the chapter. Matter refers to anything, you're not absorbing that information. You're not comprehending that information. Versus if I read, matter refers to anything that takes up space and has mass. So in my notes, I would put matter dash, takes up space and has mass. So I really, really need you to shorthand this and to make sure you're reading everything on the slide or listening to me and then putting it into your own words. I use shorthand all the time, and I really hope that you get used to that, because if you do decide to go to a larger school for college, they're not going to stop when you go, "Oh, wait a minute, go back a slide, please." They're not going to do that. So hopefully this will help you out, because I'm also not going to go back a slide, or I say I'm not anyway. I might feel sorry for you. Okay, so chapter 2 is chemistry. 2.1 is chemical elements. And just like I was reading from my book that's in front of me, that I have already read, I hope that you will also read. Matter is anything that takes up space and has mass. Okay? From anything from water we drink to the air we breathe, everything is composed of matter. It matters. What is an element? An element is all matter, living and non-living, that are composed of these. Okay, so everything is composed of elements. Each element is unique. It has its own solubility, melting point, density, things like that. So the elements on the periodic table, if you talk about periodic table, that might be where you've heard of elements before. So a few years ago, we swapped up how you took sciences, and we moved physical science, or it used to be pre-AP chemistry. I'm not sure I think some of you might have had chemistry last year. I'm not sure. But all of this should be review for you. There's 92 natural occurring elements out there. 92. So 6 of those are basic to life and make up 95% of you. 95% of you are made up of these 6 things: carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. So you can put the symbol for these if you would like. You don't have to write down the entire name of each element. If you just want to put C for carbon, but you have to know what that C means. If you have no idea, you might want to write it down. So 6 things that make up 95% of your body weight. There are other elements that are also important to life, but these are the ones that are essential or basic to life. Moving on. All right, that's just a picture of the periodic table. Miss Brown could probably tell you a million other things about this picture than I can. I just enjoy biology a little bit more than I do chemistry. I will never make you memorize the periodic table, but hopefully coming from physical science and or chemistry, a little bit of this is familiar to you. All right, so what are atoms? John Dalton come up with these guys, and he come up with the atomic theory, okay, which says that elements consist of tiny particles called atoms. An atom is the smallest part of the element that displays its properties, okay? So it's the smallest unit of matter. If I was in class right now, I would say, what's the smallest unit of life? So a lot of you, or some of you, I hope not a lot, are going to get those two confused. So atoms are the smallest unit of matter. So that doesn't mean that it's alive. Because remember, elements are like living and non-living things. Cells are the smallest unit of life. So it's the smallest unit of functioning life. Those two, there's only one word difference in those definitions. An atom and its element share the same name. Okay, and then they always have a letter or 2 letters that are used for their atomic symbol. Okay, it's just like their symbol or their abbreviation, if you want to think of it like that. So for H stands for hydrogen. Okay, things like that. So there are 3 parts to an atom. I will ask you this: neutrons, protons, and electrons. Protons are easy. So protons are positively charged. All right, so let me see if I got a picture. Okay, so neutrons and protons are found in the nucleus, in the middle of the atom. Electrons orbit outside. So neutrons are neutral. Okay, this says uncharged, but I like to say neutral because they both start with N and I can just remember it. So they don't have any charge whatsoever. They're just hanging out in the nucleus. Protons are positive. Protons start with a P. Positive starts with a P, okay? So they're positively charged. Well, what is attracted to something that's positively charged? Something that's negatively charged. So you have electrons that are outside the nucleus that are staying there because they're attracted to the proton. So the protons and the neutrons, the red, everybody look up at the screen. The red and the green, okay, the neutrons are in there. They're neutral and they're red. They're just hanging out, okay? They're not looking for a relationship here. Protons are positive, okay? So they are single and ready to mingle. So, and there must be real cute girls in there in the nucleus. So what's attracted, usually, to cute girls? Well, there's some guys out there that are like, oh gosh, there's some new kids in here. There's some new girls in here and they're really cute. So I'm going to hang around them. So that's the electrons, okay? And the electrons are usually, electrons are negative. I'm trying to give you an analogy here. But they're hanging out because they're just attracted to those protons that are positive, okay? That's how this works. And they just they don't sit in that little circle. Those are called orbitals. They don't just sit right there where they're drawn. They kind of just circle around, almost like a lion getting ready to it's just trying to get as close as it can to it, I guess, if you want to say that. So it just kind of circles around in that orbit. And if the orbit's too full, then the electrons have to go to the next orbital, which you see for that third one. I hope that makes sense. Anyways, I hope that's a review. So we have these guys. Okay, this is kind of just describing what's on the periodic table. So the atomic number is the number of protons in the nucleus. Okay, that's an easy test question to ask you. The mass number is the weight or the sum of the protons and neutrons in the nucleus. It's the mass number. But the atomic mass is usually the average of all these isotopes. So we'll kind of talk about isotopes in a minute. Isotopes don't change in their charge, but they might have another neutron hanging out, somebody that's not charged, so it's going to make it weigh more. So sometimes you have a few of those guys, and that kind of changes the atomic mass a little bit. So let's look at the picture. You have the atomic number, or the proton number, how many protons are in the nucleus. You have the symbol in the middle, and then you have the average atomic mass on the bottom, which is we would just normally say 4 for that. All right, so what's an isotope? An isotope is atoms of the same element that differ in the number of neutrons. Okay, so look up at the picture. So carbon-12, 6 protons, 6 neutrons, pretty normal. Okay, carbon-13 has 1 more neutron, so that's why its number is 13. Versus carbon-14, there's 8 neutrons. So those are isotopes of carbon. Did the charge change at all? No. Okay, just the weight. So isotopes change in neutrons. You're going to get this word confused with isomer. So come up with a way to, in your brain to figure out the difference. All right, so the periodic table. Rows of the periodic table are called periods, and columns are called groups. So let's go back. All right, rows are called periods, and those, I don't go over those that much. We don't really touch on those. Those are things that are horizontal, but we do kind of talk about the vertical columns, okay, groups, because it's easy when we start doing Bohr models and things like that. So you have your noble gases on the end that are just hanging out. They don't want to mess with anybody. Okay, so I just touch on this because it's in the book. Radioactive isotopes. So some isotopes of an element are very unstable and can be radioactive. Okay. So for example, carbon-14 changes over time into nitrogen-14. So that makes it stable. Okay, but as carbon-14 decays, it releases various types of energy, and the radiation given off by this can be detected in various ways. So sometimes, like Miss Hicks had thyroid cancer. I always tell everybody's business, especially my family, when it comes to helping out. So low levels of this radiation that can be detected, you can put a small amount in a sample and become a tracer for things. So iodine-131, this is just, you don't have to write this down, for thyroids can help because Miss Hicks, her thyroid was enlarged. So she had to drink this sample or drink this mixture, and it actually dyed her thyroid, and it got picked up because the radioactivity could be detected in her body. So the whole, it felt like a month, but I'm sure it was just like 2 weeks. Nobody got to eat salt in my family because we didn't want her to be the only one that couldn't have iodine. So we just all cut out salt, but so that was real fun. But anyway, she ended up, they did that, and they got to use these radioactive isotopes from that, and they determined that she had cancer. So high levels of radioactivity, these things can harm your cells, which damage your DNA, and thus cause cancer, okay? These things are used to sterilize your mail. And we also, coincidentally enough, we use them to kill cancer. So, cancer cells are just your cells that have went out of control and went a little crazy. All right, so electrons and energy. You cannot determine an electron's location, so we use Bohr models, okay? That's what we saw earlier with these circles and I talked about orbitals. So electron shells or orbitals represent energy levels, or the energy level the electron is in, okay? You could give a minute to keep writing. So the first shell, which is going to be the closest to the nucleus, okay, of an atom, it can contain 2 electrons, okay? So that's why in that picture earlier, you only saw 2 yellow electrons in the first orbital. I hope this is reviewed. In the second orbital, it can hold up to 8 electrons. So you're going to always fill up the first shell before you go to the second and third shell and so forth. Now there are some on your worksheets that you're going to do that Miss Brown will probably have to help you with, because some of them are a little bit larger and they're going to not go by this rule we're about to talk about. So regardless of how many shells an atom has, the outermost shell is always called the valence shell. Always called the valence shell. And it's going to determine the chemical properties of that atom, okay? So, in atoms with more than one shell, the valence electron, or the valence shell, is always called, or it's always filled up with 8. So we go by a rule called the octet rule, thus 8, okay? That's where it gets its name from. So it says, the octet rule says, let me try to see if I can read it to you verbatim so that I'm not just telling you what I think it is, like in my own words. Yeah, it's not. Okay, so the octet rule says that basically all atoms want to have 8 electrons in the outer shell, okay? Everybody wants 8 because it makes people stable. It makes atoms, I guess I should say, stable. So that they're always it's almost like being hungry, right? And you want to be full. You want to feel full. So they're always trying to reach and grab other electrons. They might borrow, they might share, in order to become full. Atoms will give up, accept, or share electrons in order for this to happen. So if in my valence shell, which is the outermost shell, if I just have 1 electron, I might just want to give it away so that my outermost electron is full. So I'm going to go, whew, I was too full. I need to give that thing away, right? It's easier to give up 1 electron versus trying to find 7 more. And this is how you get compounds, okay? Well, it's acting like I'm not connected to the internet, but I am. This is really short, guys.
Atomic structure. In this video, we're going to go over atomic structure in a very simplistic and basic way. Atoms are the basic unit of chemical elements. They contain subatomic particles in their nucleus and in the electron cloud that surrounds the nucleus. These subatomic particles include protons and neutrons, which are located in the nucleus, and electrons, which are located in the cloud or field that surrounds the nucleus. Protons have a positive electrical charge, neutrons are uncharged, and electrons have a negative charge. The number of protons and electrons are equal, so atoms are electrically neutral particles. If we look at a model of the element carbon, which has 6 protons, 6 electrons, and in most cases 6 neutrons, we can see the electrons in simple rings or shells surrounding the nucleus. Each shell represents a different energy level, and it can only hold a certain maximum number of electrons. In chemical reactions between atoms, only the electrons in the outermost shell participate in the resulting chemical bond. In atoms with only one energy level or shell, 2 electrons are required for stability. If we look at helium, which has only one shell or energy level, we see that it is full because it contains 2 electrons. So helium is stable, and there is no naturally occurring compound containing helium. Hydrogen, which also has only one ring or shell, possesses only 1 electron in its shell, so it's chemically reactive. In atoms with more than one energy level or shell, 8 electrons are required in its outermost shell.
So listen, I just said that. So 2 electrons will stay in the first one. After that, it wants 8, okay, for stability.
So neon, which has 8 electrons in its outermost shell, is stable. And oxygen, which has only 6 electrons in its outermost shell, is chemically reactive.
Okay, so it says neon has 8 in its outer shell. Does it need any more? No, right? Because you want 8. So you're not gonna see a compound really with neon in it, because neon's, it's independent over there by itself. Oxygen, rather, only has 6. So how many electrons do I need to feel, quote, in quotes, full? 2, right? So sometimes you will see H2O. So it's bound to those electrons, and then that makes water, okay? It wants 2 more.
Atoms that do have fewer than 8 electrons in their outermost shells will try to share, gain, or lose electrons in order to become stable. This is called the octet rule. But there are some exceptions, such as we saw with hydrogen and helium, which have only one energy level or shell. And that be the basics on a...
Okay. We're almost finished. All right, so the only other thing that you have to do is we're going to do some Bohr model practice. I could sit here and draw some on Cami for you, but it's just not going to be great. And maybe Miss Brown could help us out. Maybe she could draw you 1 or 2 on the board. She's probably much better at it than I am, but I will always be here for questions if you need me. Okay, so this is the end of the notes for today.